In the previous lesson, we took an in-depth look at the wave functions, probability density functions, and energies of the particle in a one-dimensional box. In this lesson, we will see what the wave functions tell us about position and momentum of the particle. When we solved the time-independent Schrödinger equation for the PIB, we found the wave functions to be psi equals square root of 2 over L times sine of n pi x over L. And the allowed energies are n squared h squared over 8ml squared, where we have chosen positive integers for quantum number n to form our complete set of solutions to the Schrödinger equation. The probability density function is the product of psi and its complex conjugate, and since our wave functions are real, it's just the square of the wave function. Recall that we postulated the formula for the expectation value, or average, of a property as an integral, which we can abbreviate like this using Dirac bracket notation. Psi is both in the bra and ket, with the quantum mechanical operator for the property in between. This means to get the average of property A, we apply operator A on psi, multiply the result by the complex conjugate of psi, then integrate over all space. Let's apply this to a very simple example. What is the expectation value for the total energy of a particle in a box if it is in quantum state n? We apply the Hamiltonian operator h hat on psi sub n, then multiply by the complex conjugate of psi sub n, and integrate over all space. Since the wave function psi sub n is an eigenfunction of the Hamiltonian operator, applying h hat on psi sub n gives us back the eigenvalue e sub n times psi sub n. Since e sub n is a constant, we can pull it out of the integral. Since psi sub n is normalized, this integral that remains is equal to 1. Therefore, the expectation value of energy for quantum state n is E sub n. If we imagine a bunch of these particles all with quantum number n, every single one will have an energy equal to E sub n. Of course, we expect the average to be E sub n. Stationary states have well-defined energy. How about the average location? The expectation value for x is the integral of psi star times x hat applied on psi over all space. For a PIB in quantum state n, here's what we get. We take psi sub n star times x hat psi sub n and integrate over all space. The x hat operator is just a multiplicative operator. It multiplies the function it is applied to by x. In standard math notation, we can write this integral as integral from x equals 0 to L of psi sub n star times x times psi sub n dx. Note that since psi sub n is real, psi sub n star is just the same as psi sub n. We can write the integral as integral from x equals 0 to L of x times the square of psi sub n dx. We can work out this integral and get L over 2. Does this make sense? You've seen plots of the probability density functions. Remember that the plots were symmetrical with respect to the middle of the box. Based on symmetry alone, we could have made a good guess that the average location of the particle is in the middle of the box, L over 2. If you want to save time in working out integrals, a good online resource that you can use is Wolfram Alpha. The site is quite sophisticated. It actually allows you to ask math questions using natural language. Here's what the Wolfram Alpha website looks like. You will see a box where you can enter your query. Here, I simply described what I wanted to evaluate. I described in words the integral for evaluating the expectation value of x for n equals 1. Pressing the enter key or clicking on the equal icon gave me this result. Note that it even tried to automatically fix a mismatched parenthesis in my query. I actually tried specifying the quantum number n first, but I could not find a way to make Wolfram Alpha assume that n is a non-zero integer. So the first answer I got was not very useful. The answer is not simple if n is not an integer. If Wolfram Alpha can't seem to handle your question, Try asking a simpler part of your question instead. For example, you can try getting an indefinite integral instead. Then you can substitute the limits and simplify the results given that n is an integer. Here's the indefinite integral for the expectation value of x. Note that if we substitute 0 and L for x, the sine and cosine expressions will just end up being 0 and 1, which makes it easy to simplify the expression. If you want to be more precise in describing your query, you can use standard math notation by clicking on the Math Input button. This will bring up an equation editor. You get tools that you can use to construct your equation. Clicking on this star brings up the most popular symbols. Here, I constructed the expression for a normalization of psi. And here's the result I got when I pressed enter. Note that if n is an integer, this part of the answer is 0, since the sign of an integer multiple of 2 pi is 0. So, as expected, the answer is 1 if n is an integer. How do we calculate the uncertainty in the location of the particle? Recall that the uncertainty expressed as standard deviation is just the square root of the variance. The variance is the difference in the expectation value of x squared and the square of the expectation value of x. Earlier, we found the expectation value of x to be L over 2. It can be shown that the expectation value of x squared is L squared over 3 minus L squared over 2 pi squared n squared. Plugging in these expressions into the expression for standard deviation, we get a standard deviation that ranges from 18% of L for n equals 1 to about 29% of L at large quantum numbers. What's the expectation value for momentum p sub x? That would be the integral over all space of psi sub n star times p sub x hat applied on psi sub n. P sub x hat applied on psi sub n means take the derivative of psi sub n with respect to x, then multiply by h bar over I. Here's psi sub n. Here's h bar over I times the derivative of psi sub n. If we evaluate this integral from x equals 0 to x equals L, we get 0. The average momentum is 0. Does this mean the momentum is 0? Not necessarily. In fact, it's not. Psi is not an eigenfunction of the momentum operator. Remember that applying p sub x hat on psi sub n gave us h bar over I times square root of 2 over L times cosine of n pi x over L times n pi over L. This is not equal to a constant times psi sub n. The fact that psi is not an eigenfunction of the momentum operator means that the momentum is not well defined. Saying that the momentum is 0 is saying that it is well defined. So what does a zero average here mean? It means that it is equally probable for p sub x to be positive and for it to be negative. What about the expectation value for the square of the momentum? Well, we can actually show that psi is an eigenfunction of the square of the momentum operator. If we apply p sub x hat twice on psi, we get back psi times a constant equal to h bar squared times k squared. Remember that k is equal to n pi over L. Since psi sub n is an eigenfunction of p sub x hat squared, the value of p sub x squared is well defined for a particle in quantum state n. The value of p sub x squared is the square of h bar k. If we substitute n pi over L for k, it's easy to show that this is equal to 2m e sub n, where m is the mass of the particle and e sub n is the energy of the particle in quantum state n. We could have also arrived at this conclusion probably more easily by remembering that the square of the momentum operator is just equal to 2m times the Hamiltonian operator. If p sub x squared is well defined, it also means that the absolute value or magnitude of p sub x is well defined. It's just h bar k or square root of 2m times e sub n. But p sub x itself is not well defined. Why? If its absolute value is h bar k, it means that it can be h bar k or negative h bar k. Earlier we said that the average value of p sub x is 0. That means that there is a 50% chance that it is positive h bar k and an equal 50% chance that it is negative h bar k. In other words, there's a 50-50 chance the particle can be described classically as moving to the right, positive momentum, and a 50-50 chance that it is moving to the left, negative momentum. The uncertainty in the momentum expressed as standard deviation is just the square root of the variance. The variance is the difference in the expectation value of p sub x squared and the square of the expectation value of p sub x. Earlier we saw that the expectation value of p sub x is 0, and the expectation value of p sub x squared is the square of h bar k. This means that delta p sub x is just equal to h bar k, or h bar times n pi over L. Earlier, we saw that the uncertainty in position, delta x, is given by this expression. Delta x is smallest for n equals 1, where it is about 0.1808 times L. Here we can also see that delta p sub x is smallest for n equals 1. This means that the product of delta x and delta p sub x is greater than 0.1808 times L times h bar n pi over L. L cancels out, leaving us with about 0.57 h bar. In an earlier lesson using commutators, we found that the product of the uncertainties of x and p sub x is greater than h bar over 2, or h bar times 0.5. This is indeed the case here for the particle in a box. Let's take a closer look at how the momentum operator affects psi. Let's rewrite psi in terms of exponential functions. Using the Euler formula, we can show that sine of kx is 1 over 2i times e to the ikx minus e to the negative ikx. Let's apply the momentum operator on just e to the ikx. Remember that the p sub x operator takes the derivative of the function, then multiplies the result by h bar over I. You should be able to show that doing so yields a constant h bar k times e to the ikx. Similarly, applying p sub x hat on e to the negative ikx yields a constant, negative h bar k times e to the negative ikx. In other words, e to the ikx and e to the negative ikx are eigenfunctions of the momentum operator. One has eigenvalue h bar k, the other has eigenvalue negative h bar k. Psi is not an eigenfunction because it is a linear combination of non-degenerate eigenfunctions. The eigenfunctions don't have the same eigenvalue. But since the square of the absolute value of the coefficients are the same for both eigenfunctions, we can say that there is a 50% chance that the particle's momentum is positive h bar k and a 50% chance that its momentum is negative h bar k. That's why we found earlier that the expectation value of p sub x is 0.